Hey everybody, welcome to your lesson on graphing the set of all solutions. So, in an equation with one variable, x, the solution will be the value that makes the equation true. So, you guys have been in middle school, you've done solving equations, and then when you find your answer, we've always taught you to go in, plug your answer in, and see if your answer equals what you solved for. And if it does, then the solution is considered a true solution. So let's look at a couple of examples. 1 is the solution for the equation x equals 1. 2 is the solution for the equation 2 to the x power equals 4. So if we plugged the number 2 in the x power using, see right here, if we plugged 2 in for that, it would be 2 squared, and 2 squared is 4. So the solution of an equation with two variables, x and y, is the pair of values, x and y, that make the equation true. So for example, 1, 2 is the solution to the equation y equals 2x because the statement 2 equals 2 is true. We would take, that would be x and 2 would be y. If we plugged in 1 for x and 2 for y, 2 times 1 is 2. 1, 3 would not be a solution because the statement 3 equals 2 is false. 3 does not equal 2. Only 2 equals 2. So the pairs of values, x, y, these are called ordered pairs, and you guys know that. And then the set of all ordered pairs that satisfy the equation is called the solution set. Sometimes there's just one ordered pair solution set, and sometimes there's more than one. So each ordered pair in the solution set represents a point in the coordinate plane. When we plot these points, they begin to form a curve. A curve is a graphical representation of the solution set for the equation. In the special case of a linear equation, the curve will be a straight line. A linear equation is an equation that can be written in the form ax plus by equals c, and we're going to really be getting into that equation a little bit later. That's called standard form. You don't have to know that for right now, just know that we're going to get into it later. Where a, b, and c are rational numbers. They can also be written as y equals mx plus b. You guys are very familiar with that. That's slope-intercept form. And that's when m is the slope and b is the y-intercept. We're also going to be going really into that. So it's important to understand that the solution set for most equations is infinite. Therefore, it's impossible to plot every single point. We looked in the last lesson, I believe it was, where we looked at lines and the characteristics of different graphs, and lines can go on forever, in which case you would have infinite amounts of points. So your solution set would be infinite. So there's several reasons solution sets are infinite. One is that there's always a number between any two numbers, and for that number, there will be a y that satisfies the equation. So when we graph a solution set of an equation, we plot several points and then connect them with the appropriate curve. The curve that connects the points represents the infinite solution to the solution set of the equation. And remember, a curve that is not very curved is just a straight line. So, key concepts. A solution to an equation with two variables is an ordered pair. Ordered pairs are always written x and y. Ordered pairs can be plotted in the coordinate plane. The path the dotted ordered pairs describe is called a curve, and a curve without curvature is called a line. An equation whose graph is a line is called a linear equation, and the solution set of an equation is infinite. When we graph the solution set of an equation, we connect the plotted ordered pairs with a curve that represents the complete solution set. Common errors and misconceptions with doing this is that believing the number of solutions an equation has is limited to the points you see on the actual graph. Incorrectly evaluating the equation for different given values. So if you plug something in wrong and you mess up how you use your integers. Incorrectly plotting ordered pair solutions on a coordinate plane. So accidentally plotting x as y, or accidentally plotting y as x, or accidentally plotting a negative when it should be a positive. Equation Our equation is y equals 3 to the x power. So I'm going to write that down on the next slide. All right, so you make a table and you plug in, you choose at least 3 values for x, and then you find the corresponding values of y by plugging into this equation. And so the values that I always like to use range from -2 to 2. And the reason for that is because it gives you a wide variety of numbers. So if x is -2, y is 1/9. If x is -1, y is 1/3. If x is 0, y is 1. If x is 1, y is 3. If x is 2, y is 9. And so there's a couple of things I want to go over with you here. If you notice, -2, y equals 3 to the -2 power. We have got to now employ our exponent rules, okay? Our exponent rules will tell us, if we don't employ the exponent rules, we will not do the math correctly. So remember from last year, you cannot have a negative exponent. If you have a negative exponent, you've got to move it to the bottom. Who remembers that? Okay, and what I mean by move it to the bottom is you now have to make this whole thing a fraction. And so what that means, you cannot have a negative exponent. In order to make it a negative, you move it, oops, I need my pen tool. You move it to the bottom, the whole thing. So it now becomes 1 over 3 to the second power. 1 over 3 to the second power is equal to 1/9, hence 1/9. Because you just simplify, 3 squared is 1/9. Okay, let's erase this ink and show you the example for -1. So we have y equals 3 to the x power. If x is -1, we do the same thing. We're going to put it over itself to make it unnegative, to make it positive. So we now have 1 over 3 to the first power equals 1/3. The last one that I'd like to review is when you have something to the 0 power. So y equals 3x, y equals 3 to the 0 power. Anything to the power of 0 is 1. Anything to the 0 power is 1, hence the number 1. Okay, so we've got now a set of ordered pairs. We've got 5 different ones from our table. Now we're going to plot those ordered pairs. And so that's where these dots, those ordered pairs come from, is from our table. Remember, always go to your x and then up to your y or down to your y. So the solution set for this, notice the points do not fall on a line. The solution set for y equals 3 to the x power is an exponential curve. That is a J curve. J curves can also look like this. They can be really straight. They can be more gradual, but J curves, anything that's not a line that looks like a J or an upside down J, is exponential. You connect your points, use arrow at each end to demonstrate that the curve continues indefinitely or infinitely in each direction, and this represents the solutions, all of them, all the solutions for the equation. There you go. Beautiful curved exponential graphed line. Example number 3 is a word problem. So the Russell family is driving 1,000 miles to the beach for vacation. They're driving at an average rate of 60 miles per hour. Write an equation that represents the distance remaining in miles and the time in hours they have been driving until they reach the beach. They plan on stopping 4 times during the trip. Draw a graph that represents all the possible distances and times they could stop on their drive. So first, we're going to write an equation to represent the distance from the beach. We're going to let d equal distance, 1,000 minus 60 times t. T is the time in hours. And the reason it's minus 60 is because they're traveling 60 miles per hour. So the trip begins at time 0. We're going to let 0 equal the first value of t. And the problem states that the Russells plan to stop 4 times on their trip. choose 4 additional values for t, and you're going to use 2, 5, 10, and 15. So using the equation d equals 1,000 minus 60t, we're going to find d for each value of t by filling in a table. All right, so we've got 0, 2, 5, 10, and 15. And then we've got 1,000, 880, 700, 400, and 100 based on the fact that we have plugged in t for each time we see t in the equation. We've plugged in those 5 numbers to get those 5 numbers for d. And the reason we're not using negative numbers in this equation, I know in the last one I said I always like to use -2, -1, 0, 1, and 2, is because we're dealing with time and we're dealing with distance, and we're not going to have a negative time or a negative distance for any question really. So once you do that, you plot your ordered pairs that you find in your table on the coordinate plane, just like we did in the last example. We're going to connect the points by drawing a line. We're not going to use arrows at the end because this line does not continue in each direction. This represents all the possible stopping points in distance and time. And there you have it, folks.